Today, we're going to be discussing the ionization of acids and bases, buffers and indicators, as well as deriving titration curves. So for your reference, here are some textbooks that might be particularly useful. Fundamentals of Analytical Chemistry, Vogel's textbook of Quantitative Chemical Analysis, and most general chemistry texts should be able to provide some useful information. So first we'll take a look at volumetric titrimetry. And this is based on measuring the volume of a reagent of known concentration, referred to as a standard, that is consumed by an analyte in a reaction of known stoichiometry. And here would be an example, where A in this reaction would represent the analyte, and B would represent the standard. In your volumetric titration, the standard is added from a burette and is referred to as a titrant, and it's being added to a solution in a flask called your titrand until there's an indication that the titrant has reacted stoichiometrically with the titrand. Now, as mentioned, in this scenario, your analyte would be A, and it would be your titrand, would be in your conical flask, and your titrant would be your standard solution, which would be added from the burette. As we mentioned, this reaction would continue until there's an indication that the titrant has reacted stoichiometrically with the titrant. And so we use indicators to help inform us that enough titrant has been added and that there is no titrant remaining unreacted. So as it relates to volumetric titrimetry, we can have different types of titration reactions. We have neutralization or acid-base titrations. We can have oxidation reduction, redox titrations, precipitation titrations, or complexation titrations. We're going to discuss neutralization titrations a bit more today. What are some of the criteria that must be met if titration is going to yield accurate and reliable results? The reaction must proceed to completion, 99.9% or greater. The reaction must be stoichiometric, so we should be able to represent it with a balanced chemical equation. And we should have a suitable endpoint detecting device, and it should be a rapid reaction so that a sharp endpoint is observed. So when we refer to equivalence point, this is a point in the titration when the exact amount of titrant has been added so that the stoichiometric reaction has been completed. And in many cases, we'll hear reference to the equivalence volume. So it's the exact volume of titrant that has been added so that the stoichiometric reaction has been completed. When we consider the end point, this is a point in the titration where the indicator changes. The goal in a titration reaction is that you're going to choose an indicator so that your endpoint as closely as possible matches your equivalence point. So let's discuss neutralization or acid-base titrations a little further. Your neutralization reactions involve reactions between the analyte and the standard reagent. The standard solution in the neutralization titrations are strong electrolytes, so your strong acids or bases, and your strong electrolytes ionize completely, whereas our weak electrolytes ionize only partially in solution. Our strong electrolytes include inorganic acids, like our nitric acid or hydrochloric acid and others, or alkali and alkaline earth hydroxides, as well as most salts. Our weak electrolytes include the weak inorganic acids, for example, carbonic acid, most organic acids, and ammonia and most organic bases. We'll also discuss the dissociation constant K, which helps to describe the position of that equilibrium as it relates to the dissociation of our weak electrolytes or weak acids and or weak bases. So just a quick reminder of some acid-base fundamental concepts. So if you recall the Bronsted-Lowry theory, it says that an acid is a proton donor, so it forms a conjugate base on proton donation, and your Bronsted-Lowry base is a proton acceptor, so it forms a conjugate acid on proton acceptance. Or amphiprotic species possess both acidic and basic properties. And of course, we have to remember pH equals minus log of your hydronium ion concentration, and pOH equals minus log of your hydroxide ion concentration. We also discussed self-ionization of water in Chem 1820. So we see where the two molecules of water are involved, and we see the production of hydronium ions and hydroxide ions. The Kw, or the equilibrium constant related to this, tells us that it's equal to the hydronium concentration times the hydroxide ion concentration. If we take the minus log of each side, what we get is the pKw being equal to pH plus pOH. And because Kw is equal to 1 times 10 to the minus 14, we see that pH plus pOH equals 14. So this is something that everybody would already be familiar with. All right, so let's look at strong and weak acid ionization. So our acids and bases are classified as being either strong or weak. Your strong acid in an aqueous solution is going to dissociate completely to give a proton and a neutral anion, and your protons are going to become associated with the aqueous solvent and produce hydronium ions, which is represented here. Your weak acid, however, is only going to partially dissociate to give a proton and an ion, and the produced anion is a weak base called the conjugate base of the weak acid, right? So we have an example of this dissociation of a weak acid here. So if we look at the figure on the right, in the first example, we see a strong acid. So the concentration before dissociation, so we see for the strong acid, weak acid, and very weak acid, the concentration is about the same. For your strong acid, we have about 100% dissociation, and we see that the equilibrium concentrations after dissociation show that we have equal concentrations of hydronium ions and conjugate base, the anion of your strong acid. For your weak acid, because we only have partial dissociation, we see that the equilibrium concentration shows that you still have some of the weak acid molecules present and equal concentrations of hydronium ion and the conjugate base. So whatever portion of your weak acid actually dissociated, each time a molecule dissociated, it would produce equal concentrations of hydronium and the conjugate base. For your very weak acid, we will see that there's close to no dissociation at all. All right, so our strong acid completely dissociates. An example would be your hydrochloric acid, and we see its dissociation in water to produce hydronium ions and chloride ions. And we see this reaction goes to completion because the chloride ion produced is such a weak base that there is little or no tendency for the reverse reaction to occur. And this can happen for the other strong acids as well. For a weak acid, like acetic acid, it partially dissociates to produce protons and its conjugate base, and we see that an equilibrium constant is used to express the relationship between the products of this dissociation and the reactant. And so the Ka for your weak acid, like acetic acid, would be the product of the concentrations of the conjugate base and hydronium ion divided by the concentration of the acid. The conjugate base of acetic acid is your acetate ion, and this acetate ion is a weak base. So if we look at its dissociation in water, represented by this equation here, this dissociation can also be expressed by an equilibrium constant, which is our base dissociation constant, which tells us that it's related to the products of that dissociation again. So the concentrations of acetic acid and hydroxide ions divided by the concentration of your acetate ion. So Kb, your base dissociation constant, would be concentration of acetic acid multiplied by concentration of hydroxide ions divided by acetate ions. Concentration of acetate ions. Your Ka of your weak acid, when multiplied by the Kb of its conjugate base, should give us Kw, right? Which, as we know, is the equilibrium constant for the ionization of water. And this is equal to 1 times 10 to the minus 14. So keep in mind this relationship. So when we look at the ionization of our strong and weak base, so your strong base is going to dissociate completely to give a hydroxide ion and a neutral cation, as shown here. Your weak base, however, is only going to partially dissociate to give hydroxide and cation. And the cation that is formed is a weak acid, and it is the conjugate acid of the weak base. So our acid or base dissociation constants. So they describe to the extent to which our weak acids or weak bases dissociate. For your acid dissociation constant, it's going to be related to the products of that dissociation, which would be the conjugate base and the hydronium ions, right? Divided by the concentration of the acid. For a base dissociation constant, it'd be related to the products again of that dissociation, which would produce your conjugate acid and your hydroxide ions divided by your base, the concentration of the base. So the tendency of your reaction to form the dissociation products is described by this dissociation constant. And you'll notice, for example, for the acidity constant, even though the dissociation typically includes water, it is eliminated from the equation described here. When we're comparing two acids or bases, there are a number of questions that we need to ask. Will higher Ka values be associated with stronger or weaker acids? Will higher Kb values be associated with stronger or weaker bases? Now, our dissociation constant describes a tendency to produce product, right? So higher Ka values means a tendency to produce more dissociation products. So higher Ka values are associated with stronger acids. For your Kb, higher Kb values will be associated with stronger bases. How else can the acid or base strength be represented? The acid or base strength can also be expressed as pKa or pKb. So your pKa would be equal to minus log of your Ka. pKb would be equal to the minus log of your Kb. Because of this relationship, as the value of Ka increases, your pKa is going to decrease. Or as the value of Kb increases, pKb is going to decrease. So for example, if we are comparing compounds, one with low pKa values to one with high pKa values, the compound with a lower pKa value would be more acidic because low pKa value suggests a higher Ka value. So it would be more acidic than a compound with a higher pKa value.